Okay, then I assume I can start, I guess.
Yes, you can.
Okay, good. So, welcome everyone. My name is Kristian Blom, and today I would like to tell you about our work, which has recently been published in PNAS, with our collaborators from the University of Texas and the Odin Institute, under the supervision of Ayaz Godek and Dmitry Makarov. And hopefully today I can convince you that ignorance can actually be bliss when it comes to estimating the entropy production rate. And does it work? Yes. And I would like to focus on the steady state entropy production, which, as you all have heard already before in other talks, quantifies the thermodynamic cost to maintain a steady state. And to evaluate the steady state entropy production, one typically needs to compute path probabilities for forward path, and also, as you can see here in the denominator, path probabilities for time reversed path, where theta indicates the time reversal operator. And when you are dealing with a Markov jump process, then this theta is straightforward, as you simply need to take literally the time reversed path, so the path backwards in time. And to narrow it a bit further down, we will focus on the steady state entropy production for Markov jump processes. And it has been shown that for Markov jump processes, you can provide a lower bound on the steady state entropy production by looking at the path probabilities of distinct states. So that means you are throwing away waiting times. And the reason why we do that is a bit delicate, but if you're interested about that, you can always ask questions afterwards. So what that means, I will look at the sequence of distinct states. And if you are then able to calculate this relative entropy here, which is denoted here in this upper formula, one has a lower bound on the steady state entropy production, given that you have a sufficiently long trajectory for which you can evaluate these path probabilities. And what is important here is that you need to, of course, know the microscopic trajectory, so the underlying Markov jump process. But for example, typically that is not the case. For example, you can have an experiment where you look at projections or you look at a finite resolution, and that means that you will not have access to your microscopic Markov trajectory, but to a non-Markovian coarse-grained trajectory, which I will indicate always with a hat. Yeah. And also for this non-Markovian coarse-grained trajectory, one, given that the trajectory is long enough, one should be able to calculate this relative entropy. And now the trick is, can we still provide a good estimation for the entropy production, given that we are looking at a coarse-grained trajectory? Now, this is a very active field of research with a lot of different results published in the last decade. For example, you can also have Markov networks where you resolve some part of the network, but not everything. So that's called partially accessible Markov networks. Or you can have a coarse-grained trajectory and try to infer back the underlying Markov process with some optimization procedure. Or you can use uncertainty relations. And what I will focus on now is coarse graining with under two types. And on the one hand, I will consider state lumping, also known as decimation, and on the other hand, milestoning. And to introduce you to both, I've drawn here a little sketch where in the middle, I have now a Markov jump network, where all the nodes are indicated with the red dots, and transitions between them are indicated with the edges. And now we can lump this process by grouping certain nodes together. And that will give rise to a lumped network, which is shown on the left, where now lumps are corresponding to the green regions. I can also look at a milestone process, and that is now on the right. And here I define certain states to be milestones, and these are indicated in dark blue. And now the difference with lumping is first and foremost that not all the states in the microscopic Markov network are a milestone, so we have certain holes in that sense. And on top of that, I will only see transitions when a trajectory enters a new milestone. So how does that work? So let me draw you a short analog trajectory. Suppose we start in this red dot here in the middle. That means we start in the lump process here. So everything which is now full color, that's where we are. And if I jump to a next state, I will make also a transition in the lump process. Then I can jump to a next microscopic state that is also corresponding to another lump. But note that in the milestone, we are still in the same state because we have not reached the new milestone yet. And finally, in the last jump, we are going to the lower left corner, and then we finally hit a new milestone. And so we see also this transition back in the milestone trajectory. And what is important here to see is that in the lump trajectory, we have now made a recrossing from the lower left lump to the middle and back. But this recrossing is actually not happening in the underlying microscopic trajectory. There you simply go to new states. And these recrossing events are a problem, a known problem of lumping that you will get because lumps share an equal border. You will have very often fast recrossing events between lumps, and this deteriorates your path probabilities and therefore your steady state entropy production. And now comes the question at hand for us. Can we use milestoning as a post-processing tool to improve entropy production estimates for lump trajectories? So the idea is as follows. Suppose you have a microscopic Markov network, which due to some, as I said, resolution or projection is now lumped. So certain states are grouped together. Can I now apply milestoning after the lumping such that I can improve my entropy production estimate? So lumping here is really a thing which you can do yourself on your computer, whereas milestoning, whereas the lumping comes really from the observation you make of the trajectory. Okay, and to show you that you actually can improve the entropy production estimates, let me start with an example of a driven single file system. So here we have a single file with a uniform bias. That means all the particles are biased in a certain direction due to Q. So when Q is not a half, you either have a preference to the clockwise or counterclockwise direction. And in this example, I have now 6 states with 5 particles, and one of them is a tracer particle indicated in dark blue. So that means that the microscopic states here, first 5 of them are aligned on a line. And if you now consider all the microscopic states, you will get a full ring. So these are all the microscopic states of our Markov model. But now, as I said, we have a tracer particle, and the idea is that we can only observe the dark blue tracer particle. So that means that certain microstates, for example, the first 5, are grouped into the same lump, and the next 5 are grouped into the same lump, etc. So in total, we've got 6 lumped positions. And now we call some of them the milestones. In this case, I call lump position 1, 3, and 5 are milestone. And now the question at hand again is, do we improve the entropy production estimates by milestoning? And what is happening here when you are milestoning, the milestones do not share a border with them anymore. So that means fast intermittent the movement between 2 lumps you do not see anymore in the milestones because they do not share a border. Okay, so let's look at the results. And for that, let me clarify how we actually evaluate our relative entropy. We do that by looking at counting sequence frequencies. And for that, we will apply a first order or second order Markov approximation. So that means that these path probabilities on the first order Markov process can be dissected into single jump probabilities, as is shown here. And if you would have a second order Markov process, they could be dissected into double jump probabilities. Okay, and these are 2 techniques we apply. And note that if the system is actually not a first or second order Markov process, these are of course approximations to the path probability. Now let's look at the result. So what I show you here in this plot is now the quality factor, which is the estimated entropy production divided by the exact entropy production for our single file system. And on the x-axis, I vary the number of vacancies. So if I have 1 vacancy, that corresponds to the example I've shown you before. And if I have 5 vacancies, we only have the tracer particle visible. And you see that in all instances, milestoning after lumping improves the entropy production estimate. You can also apply the second order Markov approximation. And also there you see that after milestoning after lumping improves or is equal to the entropy production estimate upon lumping only. And note that if you have 5 vacancies, then the system is exactly a first order Markov process, and therefore you see that our quality factor is exactly 1 in both cases. Whereas if you have only 1 vacancy, the system is exactly a second order Markov process, and then our second order Markov estimate also hits 1 with the quality factor. Finally, I would like to point out something interesting, and that is when we start to play not with the number of vacancies, but when we increase the system size for a fixed number of vacancies. So what I'm doing is I have always 1 vacancy in the system, but I'm increasing the number of sites. So that means that I have also increased the number of particles in the system, and I keep the number of milestones fixed at 3. So I always have 3 milestones. So if you increase the number of sites, the milestone distances become larger and larger. And what you now see is that if you milestone after the lumping, you get a drastic improvement of the quality factor, so of the entropy production estimate. Whereas for lumping, you see that it starts to deteriorate more and more. And in fact, we were able also to show analytically that if you take the number of sites to infinity, that under milestoning after lumping, you will exactly get 1 for the quality factor up on the first order Markov approximation. And for lumping, you will go to 0. And this is independent of how the milestones are placed, as long as you take 3. And with that, I would like to come to my conclusion that in this example of the single file, and also in other examples which are shown in the paper, we have shown that milestoning can be used as a post-processing tool to improve entropy production estimates. And in the specific case of the single file, if you place the milestones further apart from each other, which can happen by increasing system size, you get a better and better estimate. And there's one caveat to it, and that it comes at the cost of better trajectory statistics. So if you have a very large system and you have only a few milestones, you need longer and longer trajectories to better sample your jump probabilities. Now, and what is one crucial aspect which remains to be unknown is whether we can actually overshoot the entropy production rate with milestoning, because milestoning is not an injective function of the state space. In fact, it's a functional of the state space. So, and states which are not milestones, at one moment they belong to milestone A, and at other moments to milestone B. And finally, we would also like to know what is the optimal number and the placement of the milestones for a given coarse train trajectory. And with that, I would like to thank you for your attention.